This is the screencast for section 5.1, example 4. We are going to be cardiologists right now. We're going to try and measure the cardiac output of a healthy patient. Basically, we want to know how much blood the heart is outputting per second or per minute. And we don't want to have to, get a bucket and start the patient bleeding and just measure in a bucket how much blood there is. So we don't want to interrupt the flow of blood at all. We just want to know how much blood, the quantity that they're outputting, and we can use integration to do that. We can use the area under a curve, a velocity curve, to do that. So here in example 4, we're going to compute the cardiac output from dye concentration. Basically, the data in table 5.2 and the plot in figure 5, so this stuff over here, show the response of a healthy resting patient to an injection of 5.6 milligrams of dye. So we put 5.6 milligrams of dye into this patient, and we can see the dye concentration using a special machine, and then that will help us determine how much blood this heart is outputting. We're going to estimate the cardiac output of the patient whose data appear in this table and give the estimate in liters per minute. So how to do that then would be to take the total milligrams of dye, which is 5.6, and divide by the units of the area under the curve. So we have to estimate the area under this curve of milligrams per liter of the dye concentration. So your book comes up with a formula for this, and it says, okay, well, the units of the area under the curve are milligrams of dye over liters of blood times seconds. Well, let's go look at that a little bit closer. Let's look at the units of area under curve. Well, we know the area under the curve can be estimated by using rectangles. So rectangles come in the form width times length. Now the width of each of these rectangles is going to be our change in x, and the length is going to be our f of whatever x value we choose, if it's LRAM, MRAM, RRAM, either one. Now the problem though is we can't use RAM, the program in here, because we don't have a function. We don't have an f of x. We only have data points. So instead, we're going to use our graph to estimate our y values in between our x values. So between 5 and 7, we're going to use 6. Between 7 and 9, we're going to use 8. So we're going to multiply their delta x by f of the average of each x value. So by looking at our graph, it looks like the y value that might go with 6 is 1.4. 8 might be 6.3. 10 might be, 7.5. And we're going to make some very, very, close estimates. They're not going to be accurate. They are just guesses at this point. You're just kind of estimating from the graph for each of the midpoints of these rectangles, so to get their heights. Since the delta x, the change in x between each of these x values, is 2, I can factor that on the outside and just sum up all of the f of those middle x values, so all these numbers over here. And I get that that's about 55.2. Now, what's the question is, what is the unit here? Well, the delta x was in, the change in x was in seconds, the y values were in liters, and we multiplied, or milligrams per liter, so we multiplied those together, so this would be milligrams per liter times seconds. Well, that's not at all what the problem asked us to answer our unit in, plus we're only looking at the denominator here, the units of area under a curve. So we need to take the 5.6 milligrams of dye, divide it by the 55.2, so we have milligrams over milligrams per liter times seconds, and that is going to leave us with liters per second, but I want liters per minute, so I need to multiply by 60 seconds in 1 minute, and I get a total of 6.09, there we go, liters per minute. So now try problem number 15. Asks us to follow the same exact process. The following table gives dye concentrations for a dye concentration cardiac output determination. Like the one in example 4. The amount of dye injected in this patient was 5 milligrams instead of 5.6 milligrams. Okay, so we need to make a note of that, 5 milligrams instead. Use rectangles to estimate the area under the dye concentration curve, and then go on to estimate the patient's cardiac output. So again, we have a change in T of exactly 2, but now we're going to estimate each Y value, or the height of each of these rectangles, by using the X value in the middle. So at about 3, the height looks to be, I don't know, 0.4 maybe. At 5, the height looks to be about almost exactly 1. Now, of course, your estimates may be different than mine, which means in this type of a problem, your answers are going to be different than the solution manual. But I am going to make pretty close estimates using this graph. So after adding up all the heights and then multiplying by 2, I find that the area under the curve is about, because this is always an estimate when you're just guessing on the Y values here, or using rectangles for that matter. The estimate's about 45.4 milligrams per liter times seconds. Again, these are in milligrams per liter, our Y values are, and then times 2 would be the seconds. So now I'm trying to get liters per minute. So now I'm going to take the 5 milligrams that we used this time, divided by the 45.4 milligrams per liter times seconds, but that's only going to get me liters per second. I want liters per minute, so I need to multiply by 60 seconds in 1 minute, which gives me that this person's heart is outputting about 6.59 liters of blood per minute.